Good day, everyone. This is a video Properties of Hemoglobin Part 2. This is Chris, the Ancient Scholar. We'll continue talking about the basic properties of hemoglobin. Today, you guys should be familiar with the Bohr and Haldane effect. And now we're going to go ahead and combine those into something known as the Oxyhemoglobin dissociation curve. You guys that are in taking respiratory pathophysiology, you can find this in your Egan's Fundamentals of Respiratory Care 9th edition book. It explains this, but we're going to go ahead and cover it just so we're on the same page. It's actually a very important concept to understand, and the Bohr and Haldane effect will play a role in this. So what the oxyhemoglobin dissociation curve is it looks at the saturation of oxygen, or saturation of hemoglobin, what percentage of all the hemoglobin in our body is saturated with oxygen, versus what the pressure of dissolved oxygen is. Okay, and generally, what the general way it is that if I have more dissolved oxygen in my blood, the partial pressure, or not the partial, the pressure of arterial oxygen is higher, the saturation will be higher, and that's generally how it works. But there's a very, very special relationship between hemoglobin and the saturation and the PaO2, and that special relationship is called the oxyhemoglobin dissociation curve. And under normal circumstances, this is normal hemoglobin, when we talk about arterial, blood in the arterial system, normal hemoglobin will have a certain affinity for oxygen, a fairly high affinity for oxygen. And the way I always remember it is if I draw a little graph and or a little chart, and I put PaO2 on the left and SpO2 on the right. Underneath PaO2 I'll write 40, and then underneath that 50, underneath that 60. Those are my PaO2 values. And then to the right of 40 I'll write 70 under SpO2, or actually let's make that SaO2. Because the SpO2 is actually a pulse oximeter, so let's just go ahead and be proper and not start any bad habits and write SaO2 instead of SpO2, because P is pulse oximetry, A is actually the saturation that we would be looking at with an arterial blood gas. So PaO2 40, SaO2 70, PaO2 50, SaO2 80, PaO2 60, SaO2 90. Or what we call the 40, 50, 60, 70, 80, 90 rule. And that is fairly normal. If my PaO2 is 40, my SaO2 will be around 70%. If my PaO2 is 50, my SaO2 will be around 80%. If my PaO2 is 60, my SaO2 will be around 90%. And so what I've done is I've actually drawn that for you guys here. And I might have to back up just a little bit here. Alright. So if you guys look over here, I have my PaO2, 40, 50, 60, SaO2, 70, 80, 90. And sometimes they'll ask you this on a test. The patient's PaO2 is 50. What would you expect the saturation to be? And this is a really cool way of memorizing that, 40, 50, 60, 70, 80, 90. And I have actually graphed a curve. And this graph you guys see here is the oxyhemoglobin dissociation curve. So here I have saturation, my SaO2, from 0% all the way up to 100%, and then on the x-axis I've plotted PaO2 from 0 millimeters of mercury, 10, 20, 30, 40, 50, 60, 70, 80, 90 millimeters of mercury. The normal PaO2 in the body is 80 to 100, so we're looking at levels that are a little lower than normal, but that's okay, because this will actually help us understand. So what I've done is I've taken this little thing that I've drawn and I've actually plotted it here. So at 40, my PaO2 of 40, what do I have here? Well, I have a saturation of 70. At a PaO2 of 50, what do I have? I have a saturation of 80, and then a PaO2 of 60, I have a saturation of 90. Now down here I actually have a little dot, and I didn't plot that. But what that little dot is, and let's see if I can do this effectively. I don't know if I'll be able to do it, but not directly looking at it here. But what I have is this dot here, and this dot is right at about, that's 10, 20, it's right about 27. So right at about 27 millimeters of mercury, what do I have on my saturation? 50%. So under normal situations and circumstances, a PaO2 of 27 millimeters of mercury gives me an SaO2 of 50%. So 50% of my hemoglobin will be saturated at a PaO2 of 27 millimeters of mercury. That finding is what's known as the P50, and you guys will definitely see this. You've probably already discussed this in your cardiopulmonary anatomy and physiology module that you had to do earlier on in the semester, but this hopefully will bring a little more meaning and understanding to that. That the P50 is the PaO2 that results in 50% SiO2. That's in a normal person. However, sometimes hemoglobin is put into abnormal situations and circumstances. And when this happens, we will get a shift of the hemoglobin. The hemoglobin can either have a higher affinity for oxygen, it'll want to hold on to oxygen tighter and not let it go, or it can have a lower affinity for oxygen and it can just let oxygen go. It doesn't really want to transport it and carry it. Let's go ahead and talk about something called a right shift. A right shift, the way I remember this is right shift is a release of oxygen. So if the hemoglobin is right shifted, it releases oxygen, has a low affinity for oxygen. It does not want to bind oxygen. The things that cause hemoglobin to release oxygen are raised temperature, just think of R's, raised temperature, raised acids, so acidosis, reduced oxygenation, and raised something known as 2,3-DPG or 2,3-diphosphoglyceride. 2,3-DPG is a molecule that helps hemoglobin release oxygen, go figure, right? And certain patients, like people with COPD, often can have elevated levels of 2,3-DPG due to their disease process. So chronic obstructive pulmonary disease patients are often right shifted. Their hemoglobin has a reduced affinity for oxygen and it wants to release oxygen. Okay? There's also something called a left shift. And a left shift, the way I think about a left shift is it locks oxygen. Left is lock oxygen or an increased affinity for oxygen. So left shift, the hemoglobin holds, think of hold, the L, and hold oxygen. Increased affinity, hold oxygen. Well, what causes a left shift? Just the opposite of a right shift. Low temperature, low 2,3-DPG. Patients, trauma patients that receive massive transfusions will end up having low 2,3-DPG. Alkalosis. If you're very alkalotic, let's say you have a head injury and you hyperventilate the heck out of them, you can put them into a left shift. The hemoglobin will lock onto that oxygen. It won't necessarily want to give the oxygen up. And then lots of carbon monoxide poisoning from house fires and such can cause a left shift or a increased affinity for oxygen where hemoglobin locks. So we don't ever want to go into total left and total right shift territory. We like to have our hemoglobin hold on to oxygen in the lungs and release oxygen at the tissues. Now, if it's left or right shifted, it's not going to do that normally, and that can potentially cause problems with oxygenation. So if we go back to the little drawing here, hopefully these colors show up well, but I actually have this purple color here, and this is an example of right shifted hemoglobin. So you can see that the hemoglobin here has a decreased affinity for binding oxygen. It does not want to bind oxygen as easily as the blue line, a normal oxygen. Over here, I have this green line here, and this green line is left-shifted hemoglobin, and this is hemoglobin that has a very high affinity, and you can see that the hemoglobin is binding oxygen very readily, but because it has an increased affinity for oxygen, it's not necessarily going to want to give that oxygen up. So this is another case where my saturation may be high, but that doesn't necessarily mean that oxygen is getting to the tissues where it belongs. So again, saturation and pulse oximetry And the SaO2, of course, ultimately can be misleading.